let us take the second model of question. See, the question is, an element A has 3 electrons in the valence shell. Right. Another element B has 6 valence electrons. Formula of their compound is, okay, so this is a question. Come on. You know, A has 3 electrons in the valence shell, and B, of course, has 6 electrons in the valence shell. Now let us take this information and write their valences, then go for crisscross method. See, the number of valence electrons in A it is 3, whereas in B it is 6. See, from the number of valence electrons, we can say the group number of element. You know, because A has 3 electrons in a valence shell, I can say that it belongs to third A or 13th group. Because B has 6 electrons in the valence shell, you know, it belongs to 6th A group or 16th group of long form of periodic table. Now let me tell you an important point here, that valency of an element can be given as equal to group number. But here the condition is only when the group number is less than or equal to 4. This is when valency can be straight away taken as equal to group number. Now coming to the second point, valency of an element can be given as 8 minus group number. I mean the combining capacity, provided group number is greater than 4. Okay, so based on this particular rule, I hope we can now go for the next step. Come on, valency of A can be given as equal to 3. I told you that the valencies are generally represented using the Roman numerals. Okay, but because every time we cannot go for the Roman numerals, only for convenience sake, I am using the regular one. Coming to the valency of B, it falls under this category where the group number is, of course, greater than 4, right? Group number is 6th A, 6 is what you have to consider. So in such a case, you know, valency can be given as 2. Don't consider the group number as 18 or 16 or 13 like that. This is, of course, say third group, of course, third A. Say 6th group, of course, 6th A. Don't say 13 and 16. You cannot subtract 13 and 16 from 8, right? So little careful, you need to. Come on, that's it. I got the valencies and now I can go for crisscross. Come on, this is your formula. The formula of the compound can be given as A2B3. Only 3 steps. They have in fact given the number of valence electrons, based on which we have written the group number. And from the group number, we have written the valence. So this is how you have to solve questions of this type. See, in this itself, I can actually give you different models. Let me give you some more. Now, rather than giving the number of valence electrons, sometimes electronic configuration is given. Check this out. Electronic configuration of an element. X is 1s2, 2s2, 2p6, 3s2, 3p1, and that of y is 1s2, 2s2, 2p6, 3s2, 3p5. Formula of the compound formed from X and Y would be, what would be the formula of the compound formed from these two? Now let us consider the electronic configurations. You will of course have one extra step here. Come on. Consider the electronic configuration of X. 1s2, 2s2, 2p6, 3s2, 3p1. Coming to Y. 1s2, 2s2, 2p6, 3s2, 3p5. Now, check this out. So this is the valence shell. Nothing but N. Now this is your penultimate shell, right? And finally, this is anti-penultimate shell. This is N-1, and this, of course, is N-2. Now, coming to this is your N, I mean the valence shell. This is N-1, and this, of course, is N-2. Right? Now, let us actually write that this is the electronic configuration given. Now, from this, can we write the number of valence electrons? Yes, of course. The number of valence electrons in X can be given as 3, clearly visible. Now, the number of valence electrons in Y can be given as 7. Now, let us go for group number. The old type of group numbers. This belongs to 3rd A. This belongs to 7th A. Right? Now then, come on, let us write the valency. You know the valency of this is of course 3 because it comes under the first rule, where the group number is less than or equal to 4. Of course, it is less than 4. Coming to the second one, it comes under the second rule, where the group number is greater than 4. You have to calculate valency using the formula 8 minus group number, right? That's it. You got your valencies. Come on, go for Criss cross method. That's it. So the formula of the compound can finally be written as X1, Y3 or simply XY3. So the only extra step that is given in the problem is the electronic configurations are given. Of course, we know that the final shell or the last shell is called the valence shell. Last but one is penultimate. N-2 is called anti-penultimate. Okay. Now let me also give you one more model. Of course, a different kind of electronic configuration. Okay. Electronic configuration of an element X is 282. They have given K, L, M, N type of electronic configurations. Of course, we are familiar with that. And Y is 287. Formula of their compound is. Okay. Now let us go for this. Come on. Electronic configuration of X, electronic configuration of Y. Now take the electronic configuration. 282, 287. Of course, the given configuration is K, L, M, N type of method. Now this is the valence shell. This, of course, is penultimate. And this is anti-penultimate. Even here also, N, N-1, and then this is N-2, right? Now, come on, let us go for the number of valence electrons first. Coming to the number of valence electrons, check out the number of electrons present in the nth shell. Now, from this, we can write the group number, right? So the group number of X can be given as second A, and Y, of course, is 7th A. The old format. This, of course, is second group. As per the new format, this, of course, is 17th, but we use the old one. In order to use the formulae given, we will just go for the old one. Now, coming to valency, because anyway, we got the group number. Valency of this is equal to 2 as per rule number 1, because the group number is less than or equal to 4. I mean less than 4. In this particular case, it is, of course, 8 minus 7, because the group number is greater than 4. Right? That's it. Go for Criss-cross method. The formula can, of course, be given as XY2. Okay. Now, let us take one more question wherein atomic numbers are given. The atomic number of an element A is a 16 and that of B is a 19. This is interesting. Formula of the compound of X and Y is okay. Come on. Atomic number of A is 16 and that of B is 90. Let us write the electronic configurations. I think, yeah, let us go for things one by one. Coming to the atomic number of A, it is a 16 and that of B is 90. There is some twist in this problem. Let's see what that is. Coming to the electronic configuration, one more extra step. This, of course, can be written as 286, or else if you want, this is, of course, 1s2, then 2s2, 2p6, then this is 3s2, 3p4. Right. Coming to this one, this, of course, can be written as 2, 8, 8, 1. Come on. This is 1s2. This is 2s2, 2p6. This, of course, is 3s2, 3p6. Then go for the fourth shell, that is 4s1. Right? Okay. Now, let us go for the next step. Coming to the number of valence electrons. Now, in this, the number of valence electrons is 6. And in this, the number of valence electrons is just 1. Isn't it? So, here the number of valence electrons is 6. And here, the number of valence electrons is 1. So, this is what is actually interesting here. Remember, metals generally possess lesser number of valence electrons. Let me say 1 to 4. Whereas non-metals possess more number of valence electrons. I mean 5 to 8. So which one is a metal here? It is very clear that this is a metal. And you all know that the metals generally form cation. And say this is a non-metal. Right. Non-metals generally form anions. I told you this. Now coming to the group numbers. Yes, of course. This belongs to 6th A and this belongs to 1st A. 1st A are called alkali metals, I told you. And 6th A are of course called chalcogens. Now from this we can write the valence. Come on. See, in case of this, the valency can be written as 8 minus 6. Whereas in this case, the valency can be written as 1. This according to rule number 2. This according to rule number 1. Right. Now coming to the last step. Criss-cross method. But you know, while writing the formula, you need to be little cautious. It is because the cation is generally written first and the anion just follows it. So it has to be B2A. Remember, it cannot be A1, B2 or AB. It has to be B to A. So this is very important. Remember, cation is written first. Followed by anion. Got it? So that is a different model again. This way, we can go for different varieties. See, symbols for some elements were given considering the name of the country or the name of the city, the names of states, or the names of continents also. Let me give you some examples. You know, based on the name of the continent, there is an element called Europeum. Europe, of course, is the name of the continent, right? The symbol of Europeum is given as EU. Okay. Then there is Americium. This, of course, has come from the name of the country, America. And the symbol goes this AM. Now, there is a state in America called California, on the basis of which an element is named as Californium. And this, of course, is given the name based on the name of a state in America. Coming to the symbol, it is a CF. Now, there is a city called Berkeley, based on which an element is named as berkelium. So this can be given as BK. Okay, so based on continent, based on the name of a country, based on the name of a state, based on the name of a city. All right. So this way, elements were given symbols. Now, some elements were given symbols based on the names of scientists. Of course, many elements were given based on the names of scientists. We all know the name of a scientist, Alfred Nobel, on whose name an element was named as nobelium. Name of the scientist is Alfred Nobel. Hope you know that every year Nobel Prize is given in different fields for the scientist who has done marvelous work or research in a particular field. So in this case, the symbol is given as invoke. And there is one more scientist, of course. Einsteinium. One more scientist. The name of the scientist is Albert Einstein, isn't it? See, the name of the scientist is Albert Einstein. Based on his name, an element is given the symbol ES. So this way, many elements are given symbols based on the names of the scientists. Now, there are certain elements which were, of course, given their symbols based on the names of planets. Right. Let me tell you that there is an element called uranium, named after a planet Uranus, symbol for which was given as U. There is an element called plutonium, which was named after Pluto, and the symbol was given as Pu. There is something called neptunium, which was, of course, named after Neptune, NP. Yes. Now, the most important symbol given by Iupac, very important. Let me give you some basic information on this. Iupac stands for International Union of Pure and Applied Chemistry. You can also say that it is International Union of Pure and Applied Chemists. It is a union of chemists, right? Now, Iupac has actually given some three-lettered symbols. Three-lettered symbols were given by Iupac. In order to write these three-lettered symbols, you need to know some basic information. First one, supposing if the atomic number, of course, has a number 0. I mean, if there is a number 0, if there is a 0 in the atomic number, just say nil, 0, nil, 1, we call it un. If it is a 2, if the atomic number consists of the number 0, we call it nil, 1, un, 2, say by. And if the atomic number has this number, we say tri. 4, of course, is called a quad. 5, pent. 6, hex. 7, sept. 8, oct. 9, n. Okay. So these are used for writing the 3-lettered symbols of elements with atomic number generally more than 100. Even if not discovered, they just go with these things. Let me give you examples. Now suppose you want the IUPAC name of an element with atomic number, say 104. We know that 1 is called un. People also say an. Okay, un. And how about 0, nil, isn't it? Going for 4, quad, right? 1 is un, 0 is nil, and then this, of course, 4 is quad. Finally, you just write em. So it can simply be written as un nil quad em. And the 3-lettered symbol can be given as this. The first one must be a capital one. The remaining 2 must be the small one. Un nil quad em, isn't it? Now go for, say, 108. What is that? Un nil oct em. It can be written as un nil oct em. UNO. Now suppose if the atomic number given is 112, how do you write that? Un by em, right? Now there is some twist here. While writing the name of this, un by em, isn't it? But here you can just omit 1 I. So what do you write that? Un by em. It's not by em, by em. So the symbol of this can be given as UUB, un by em. Suppose if the atomic number is, say, 190. Let's see. 1 un, 9 n, then nil, then em. What do you write? Un n nil em. Look at this. Even here also, you know, 1 n is omitted. You can just omit 1 n. What do you write? Un n nil em, and the formula can be given as U E N, un n nil em. That's it. So these are the two special cases. The remaining are normal. Now I think you got my point. So these are some of the elements for which three-lettered symbols were given by IUPAC. Okay.